Alright, what's up everybody? So in this video I'm going to be covering basically everything in lecture 2. Some of the topics we'll be covering is the periodic table, valence shell electrons, electronegativity. I'll also go into why electronegativity and atomic size kind of go hand in hand and how they relate to each other. We'll talk about covalent bonds, non-covalent bonds, and hydrophilicity, hydrophobicity, and maybe a couple things off the cuff while we're going through all that. So we're going to start with reading the periodic table, and all of these are just slides that I've pulled out of the lecture. Alright, so when we're looking at this, you'll want to look at your groups. And you can kind of think of them as being numbered as such. And remember that every element wants to have a full valence shell. So all of these right here are going to want to have 8 in their valence shell. So if we look down to this area, we can see, let's go to carbon. We know that carbon always makes 4 bonds. And if you're wondering why carbon always makes 4, it's because, well, one, it's a group 4 element. And then if you want to conceptualize that further, you can go down here and you see that it has 4 valence electrons right here. It's going to want to pair all of those up and have a total of 8. So with this hydrogen, if we were to look at a hydrogen molecule, it would look like something like this, with 1 electron. So it's this 1 electron is making a bond with each of these to make these bonds right here. And in doing so, carbon meets the octet rule. Everything's good. And when you get into structural stuff, we'll jump ahead a little bit. You're going to want to know that carbon always needs 4. So we have 1, 2, 3, 4. And we'll get back to this in a second. I don't want to jump around too much in this. So the next concept we're going to talk about is electronegativity. So it says here, electronegativity is a chemical property that describes the tendency of an atom to attract electrons towards itself. And so I've mentioned this a few times in other videos. Let me find a color that will work really good on this. So the reason that there actually is partial negatives and partial positives is because oxygen, we'll say it has some protons in its nucleus. And over here, hydrogen also has a proton in its nucleus. Well, the wall, I guess we could say the electron probability of an electron being here is a lot less. So the distance between this proton of the core of this hydrogen in this area over here is a lot smaller. So it's getting a lot more of that partial positive from the interior of that atom. Where this one, this distance is a lot farther, which is why it's going to appear as partial negative, because we have a lot more negativity over here due to all this electron density. So when it comes to bonds, we have ionic and non-ionic. Sorry, we have covalent and non-covalent. So we're going to throw covalent over here, and we're going to throw non-covalent over here. So in your covalent bonds, it's going to be things that are hooked to each other. Anything that looks like this is covalent. That's not a hydrogen bond. This is an oxygen. These are covalent bonds. So just know that. Obviously, this would be a non-polar covalent, and this would be a polar covalent. So just understand that a covalent bond is the molecules are actually hooked to each other because they're sharing those electrons. And then obviously in your covalent you have non-polar covalent and you have polar covalent. So just always keep an eye on that and don't get mixed up on the test for that. In non-covalent, you're going to have ionic bonds. You're going to have hydrogen bonds, and then van der Waals. So anything capable of hydrogen bonding, the main ones are NH, OH, and FH. And remember, your hydrogen bond is going to look like this. It'll have that dashed line. So those are hydrogen bonds. This is not a hydrogen bond. This is not a hydrogen bond, not a hydrogen bond. Alright, so I think we did well on that. And then an ionic bond is going to be any charged atoms that join together and neutralize each other. So for the structural formulas, I just wanted to draw these in other ways that you could possibly see them. So this one could also look like that. It could also look like that. This one could look like this. It could also look like this. For this one, I'm just going to draw, boom. So this is that. This is that. This is that. This is also that. This is that. This is that. So look at this slide. If you're confused about what I just did and why that is what it is, draw these structures on paper, then draw this one, and then draw this one, and then try to understand, okay, this carbon is here, this carbon is there, this one is there, this one is there, this double bond is this double bond, and just go through and do that to all of them. This carbon is this carbon, this carbon is this carbon. So some of you are going to get this right off the bat, which is really good for you, and then other people are going to struggle with conceptualizing this, and that's normal. I would say you're in the majority if that's the case. So just work on it. The only way you're going to get better is to keep drawing it. Alright, so on this question, it's asking which one is more soluble. So when we think soluble, we think hydrophilic. When we think hydrophilic, we think polar. So just write soluble equals hydrophilic equals polar. So when we look at this, what is the polarity we see? Okay, so we have some polarity around this nitrogen. Okay, so we'll say one region of polarity. So we go over here. We have one region there, one region there, one region here. 3. So this is obviously this one is more polar, so it's more hydrophilic, which means it's more soluble. So if we were to throw these two in water, since drug 2 is more polar and hydrophilic, this image right here is going to represent drug 2. This one will represent drug 1. And just know this is caused by the hydrophobic effect. And that's the whole reason this happens spontaneously is because it's an increase in entropy. And entropy is a measure of disorder. So if you look here, if you were to separate these and put water around each of them, there'd be a lot of water around all of these. We have 3 complete water shells, where by them joining each other, we only have, it's bigger than 1 water shell, but it's a lot smaller than 3. And by doing this, we have a lot more water that can float all around here. There's more water all over the place. And that's an increase in disorder. There is more disorder in this system now because of this. There's water everywhere. Sorry, this pen looks cool. So yeah, that's basically how the hydrophobic effect works. And if anybody is interested, the hydrophobic effect, what is it? Change of H minus T, change of S. And this is basically it. This is your entropy. Alright, so that's it. I'm going to try to keep all these videos under 10 minutes. So I'm going to go ahead and review lecture 2 and then post a video about lecture 2.